Menon, Assistant Professor, Department of Mathematics, Government College of Engineering, Srirangam, Trichy. This video is for BE Computer Science students, third year paper, MA8551, Algebra and Number Theory, Unit number 2, Finite Field and Polynomials. Lecturer video number 7, GCD and Euclidean algorithm for polynomials. This is for polynomials only. Now we define monic polynomial. A polynomial f of x belongs to f of x is called monic if its leading coefficient is 1. That is the unity of f. Example, x squared plus 4x plus 6 belongs to z7 of x is a monic polynomial whose coefficients are in z7. The leading coefficient is 1. Therefore, it is monic polynomial. The second example, x power 5 plus 3x squared plus x plus 4 belongs to z5. Its coefficients are belongs to z5. Therefore, it is the polynomial in z5 of x. The leading coefficient is 1. Therefore, it is monic polynomial. The third example, 3x squared plus 2x plus 7 belongs to z13 of x, whose coefficients are belongs to z13. Therefore, it is a polynomial. But its leading coefficient is 3. Therefore, it is not a monic polynomial. The next definition, greatest common divisor of two polynomials. If f of x and g of x belongs to f of x, then h of x belongs to capital F of x is a greatest common divisor of f of x and g of x. What are the conditions? Condition number 1, if h of x divides each of f of x and g of x. F of x divides both these functions. That means these two polynomials. And also, if another one polynomial k of x, which is divides both f of x and g of x, then k of x is also divides h of x. Then h of x is called greatest common divisor of f of x and g of x. This is the condition for GCD. This is the definition for GCD. Design two more questions. Define GCD of polynomials. Then the theorem, let f of x, g of x belongs to f of x with at least one of f of x and g of x, not the zero polynomial, Then each polynomial of minimum degree that can be written as a linear combination of f of x and g of x. That is the form of s of x into f of x plus t of x into g of x. That is the linear combination of f and g. Here sf plus tg. For some s of x, t of x belongs to f of x will be the GCD of f of x and g of x. Which one is GCD? This linear combination is GCD. If we require the GCD is to be monic, then it will be unique. If GCD is monic, then it will be unique. Otherwise, it not will be unique. Proof. First, let capital S is the collection of the linear combination of these functions. Collection of these polynomials. Let S equal to S of x into f of x plus t of x into g of x, such that S of x and t of x belongs to capital F of x. First assume if S is not equal to empty, S is not equal to empty, then what is the condition? S is not equal to empty. Then either f of x and g of x not will be the zero polynomial, which is the assumption. We choose f is non-empty, then s is non-empty. Let t of x be a polynomial with least degree in s. in this polynomial, in this collection of s, we assume t of x be the least degree polynomial, least degree polynomial in s. Therefore, every element in s is of the form this. Therefore, t of x is equal to some s of x into f of x plus t of x into g of x. Let us assume this term. Okay. First we prove that t of x is the GCD. T of x is the GCD of f of x and g of x. Now consider, what is the condition for GCD? The term divides both f and g. Now first we prove f of x and t of x. By the division algorithm, f of x equal to f of x is the greatest value. So f of x equal to some q of x into d of x plus some remainder it have. So q of x into d of x plus r of x, where either r of x equal to 0 or degree of r of x equal to degree of r of x is less than degree of d of x by the division algorithm. Therefore, r of x equal to the remaining terms taken to the right side. So r of x equal to f of x minus q of x into d of x. We know that we assume d of x is equal to s of x into f of x plus t of x. This is the first assumption we assume. Multiplying this q of x into inside, we get this term. It is f of x, it is also f of x. Take this 1 minus q of x into s of x into f of x. This minus of plus minus q of x into t of x into g of x. It is the some terms multiplication of f of x, some terms multiplication of f of x, and also some terms multiplication of g of x. So it is of the form s of x into f of x, some t of x into g of x. Therefore, r of x is also belongs to s. If r of x is not equal to 0, then what is the previous condition? Degree of r of x is less than degree of d of x. Why? Degree of r of x is less than degree of d of x by the previous page, which is contradict to the choice of d of x. What is the condition of d of x? D of x is the least degree polynomial in S. Here r of x is the least degree. Why? Here the condition says. Therefore, r of x is not equal to 0 is contradiction. Therefore, r of x equal to 0. Then r of x equal to 0, we get f of x equal to g of x into d of x. Therefore, d of x divides f of x, since f of x is the multiplication of these two. Therefore, d of x is divides f of x. Similarly, we can prove that d of x divides g of x. Okay, d of x divides both f of x and g of x. The another one condition. What is the second condition? If another one polynomial c of x divides both f of x and g of x, then c of x is also divides d of x, which is the we want to prove. Now c of x divides f of x, which implies f of x into some polynomials multiplication is also divides, and also g of x is divided by c of x. So we multiply some functions with s of x is also divides c of x. C of x is divides these functions is also. If c of x divides this and this, then c of x is also divides these two sums. Therefore, what is this value? It is the d of x. Therefore, c of x divides d of x. Therefore, d of x is the GCD of f of x plus g of x by the GCD definition. Hence the proof. What is the other one condition? The last condition is if it is monic, then it will be unique. If GCD is monic, then the GCD is unique. Suppose d of x equal to a0 plus a1x plus a2x square plus etc. an x power n. an x power n with an is not equal to 0. an is not equal to 0. Then multiply this term by an inverse. What will we get here? An inverse into an. Multiplying these terms, each and every term, we multiply by an inverse in pre-multiply. We get an inverse an is identity, so it is 1. So 1. Therefore, it is a monic polynomial. It is a monic polynomial. Therefore, an power minus 1 into d of x is a monic polynomial. D of x is a GCD, then an inverse is also GCD. Some constant multiplication is also GCD of these two terms. Suppose d1 of x and d2 of x be two monic polynomials which are also GCD of f of x and g of x. Let us assume this one. If d1 divides d2, since these two are monic polynomials, these are GCD. Now d1 of x divides d2, treating t2 as GCD. So it is GCD. So d1 is smallest value. Therefore d1 is divides d2. If d1 is GCD, then GCD is bigger. So t2 of x divides d1 of x. Therefore, these two are only possible when d1 equal to identity into d2. d1 equal to d2. What is here? U. U is the multiplicative identity. That means unity. U is unity. Unity of f. Since both d1 of x and d2 of x are monic polynomial, these are two monic polynomials, then u equal to 1. U equal to 1. Therefore, d1 equal to d2. Therefore, GCD is unique when it is monic. When it is monic, the GCD is unique. Hence the proof. Then Euclidean algorithm for polynomial. Euclidean algorithm for polynomial. Let f of x and g of x belongs to capital F of x with the degree f of x less than or equal to degree of g of x and f of x not equal to 0. By applying division algorithm, we write g of x as the multiplication of some quotient into f of x plus remainder r of x with degree r of x is less than degree of f of x. Then we rewrite f of x as the multiplication of r of x, this term, into q1 of x plus some remainder r1 of x. Here r1 of x is less than degree of r of x. Then we write r of x as some multiplication of r1 of x into q2 of x plus r2 of x. Here r2 of x degree is less than degree of r1 of x. Similarly, we can rewrite these terms as rk minus 2 of x is equal to some qk of x into rk minus 1 of x, rk minus 2, so rk minus 1 of x plus rk of x, where degree of rk of x is less than degree of rk minus 1 of x. And rk minus 1 of x is equal to q k plus 1 it is qk. So the next one is qk plus 1 of x into rk of x plus rk plus 1 of x, where rk plus 1 of x equal to 0. We obtain this Euclidean algorithm up to the last remainder will be 0. Then rk of x, it is 0, but rk of x is last non-zero remainder, is last non-zero remainder. It is the last non-zero remainder. The last non-zero remainder, the last non-zero remainder is called GCD of the given two polynomials. Given two polynomials. The last non-zero remainder is called the GCD of the given two polynomials. It is an important result. And is a constant multiple of the monic greatest common divisor f of x and g of x. Multiplying r k of x by the inverse of the leading coefficient allows us to obtain the unique monic polynomials we call greatest common divisor. Relative primes. If f of x and g of x belongs to f of x and their GCD is 1, if the GCD is 1, then the given polynomials are said to be relative primes. Then the polynomials are said to be relative primes. Example, using the Euclidean algorithm for the polynomials to find the GCD of each pair of the polynomials over the designated field f. Then write the GCD as s of x into f of x plus t of x into g of x. We write GCD equal to this type, where s of x and t of x belongs to f of x. Here f of x is equal to, here f of x equal to x power 4 plus x cube plus 1 and g of x equal to x squared plus x plus 1. What is the largest value? What is the smallest value? X power 4 is largest polynomial, x squared is smallest degree polynomial. So we put x power 4 inside x power 4 plus x squared plus 0x squared plus 0x plus 1. Here x squared. X squared into x squared equal to x power 4. So multiplying these two values, we get x power 4 plus x cube plus x squared. Then subtracting, we get these two terms cancel, these two terms cancel. This is minus x squared. So minus 1. Minus 1 into this term will be get, take this down. So minus x squared minus x minus 1 is equal to x plus 2. Here the coefficient is r in z2. We write minus 1 is equal to plus 1. Here the simplifying the last term is what? X plus 2. It is equal to 2 is what? 0. So x plus 0. Therefore it is x. So it is equal to x. Therefore x power 4 plus x cube plus 1 can be written as these two terms multiplication plus a remainder in z2 of x. It also can be rewritten as x squared plus 1. This is no problem. Okay, then by using division algorithm, again we get what is the quotient, what is the previous divided term, x squared plus x plus 1. What is the remainder? X. We divide these two, we get the quotient will be x plus 1. X into x, x squared. So minus this term is eliminated. Then we down these terms x plus 1. Then 1 into x is x. So subtracting, we get this term eliminated. Then the remainder is 1. Therefore x squared plus x plus 1 equal to x into x plus 1, x into x plus 1 plus 1. Then x plus 1 is equal to multiplication of this value. X plus 1 equal to 1 into x plus 1 plus remainder is 0. Therefore the last non-zero remainder is 1. From this step, The GCD is 1. From this step, 1 is equal to what? 1 is equal to what? By 1 is equal to, take these two terms to left side. X squared plus x plus 1 minus x plus 1. It is equal to, by 1. What is the value of x? What is the value of x? The previous equations, its value be x power 4 plus x cube plus 1 minus x square minus 1 into x square plus x plus 1 into this term. This term is this term. So again multiplying x plus 1 inside. And simplifying we get this terms is, what is its coefficient here, minus here x plus 1. So minus x plus 1. Its coefficient is minus x minus 1. Then another one term, this term. What is its coefficient? Here 1. Here multiplying these two terms, we simplifying we get this term. So after simplification we get GCD equal to product of the given two polynomials. Product of the given two polynomials. What are the given two polynomials? This polynomial and this polynomial are given. So it is the S of x, it is the T of x. It is GCD. GCD equal to S of x into f of x plus T of x into g of x. Thank you.